When an internal combustion engine is used, it must often be disconnected from the drive wheels in order to keep the engine running while the vehicle is not in motion. Then, to start the vehicle smoothly, the power from the engine must be connected to the drive shaft gradually. This is usually done by a friction clutch operated by a pedal. The driver must release the pedal slowly to apply the power gradually and not strain the engine or other parts of the vehicle. The smooth application of the clutch plates to allow the engine to take hold slowly and smoothly requires considerable skill on the part of the driver. On certain modern vehicles, this operation is done automatically by means of a fluid coupling. How can this coupling of engine to drive wheels be accomplished by means of a fluid or liquid? Well, we know that any liquid under pressure has a certain force or energy, and it is this energy that is utilized in the fluid coupling. Here we've set up a model of a fluid coupling on a simulated drive shaft to show how the fluid coupling is positioned between the engine, the transmission, and the drive wheels. To see how the fixed mass of liquid inside can be used to couple the engine to the drive wheels, let's take a look at this bowl filled with a liquid, in this case, oil. When the bowl is revolved, the clinging quality of the oil causes it to revolve also. As a result, the centrifugal force set up causes the oil to move from the center to the outer circumference and creep up the sides of the bowl. By attaching a set of vanes which radiate outward from the center to the bowl, we can increase the tendency of the oil to rotate with the bowl. This causes more energy to be transferred from the bowl to the liquid. Now let's see what happens when we add a second set of vanes. Notice that this set is not connected to the bowl or lower set in any way, but can move freely. The shaft, which has a marker to show rotation, can be likened to the drive shaft of a vehicle. The upper set of vanes doesn't revolve at first because the bowl isn't imparting enough energy through the oil to overcome the resistance of the hand holding its shaft. As the speed of the bowl increases, more energy is transmitted, causing the upper set of vanes and its shaft to revolve, despite the load exerted on the shaft by the hand. This pressure of the hand can be likened to the load the engine must move. The lower set of vanes is called the pump, the upper set, the turbine. We've seen the transmission of power without a mechanical connection between the two sets of vanes, but just by means of a fixed mass of moving liquid. To put this method to work on the drive shaft of a vehicle, which instead of running from the bottom to the top runs horizontally, from the engine to the drive wheels, the fluid coupling must be a sealed unit and have a leak-proof housing. Here's the actual fluid coupling, which has been disassembled so you can see inside. This is the driving member which connects to the engine. It's called the pump and has straight vanes radiating from the center to the rim. Note the addition of this ring. Its purpose is to better control the flow of fluid within the pump to the driven member. For that reason, it is called the guide ring. And this is the driven member, which connects to the drive wheels. It's called the turbine and is constructed almost identically to the pump, including the straight radial vanes and guide ring, which better directs the oil back to the pump. By using this pipe cleaner, we'll be able to see how the centrifugal force sends the fluid from the pump to the turbine and back again. This pipe cleaner, representing the oil in the fluid coupling, is now ready to show this motion, which is called the vortex motion of the oil within the fluid coupling. Because of the guide ring, uniform, non-turbulent vortex flow results, increasing the efficiency of the coupling. Now we know that there is this direction in the oil within the fluid coupling. But we also know that the pump is turning, so there is another direction that the oil takes, which goes this way. Therefore, the effect of this dual motion in the oil would be roughly in this direction. Because of the centrifugal force and the turning of the pump, the actual flow of oil is like a continuous corkscrew that goes round and round inside the fluid coupling in operation. It must be remembered that since the fluid coupling only replaces the conventional clutch, it is always used in conjunction with some type of transmission. Now that we know the parts of the fluid coupling and the way it operates, let's see it in action on a vehicle. At first, with the engine idling, it turns the pump so slowly there is not enough energy transmitted to overcome the inertia of the vehicle. As engine speed increases, the pump turns fast enough to transmit the required energy through the liquid to the turbine and on to the drive wheels. The vehicle now moves. Soon the turbine tends to catch up with the pump as the vehicle rolls along at higher speeds. When the driver releases pressure on the accelerator, the momentum of the vehicle tends to keep it moving at the same speed. This causes the pump to slow down, but not the turbine. In other words, the turbine overruns the pump, and because it's built almost exactly like the pump, the turbine will transmit energy back to the pump. In effect, the turbine tries to drive it. Engine compression, however, resists this attempt of the turbine to drive the pump, and results in the vehicle slowing down, such as would happen with a conventional clutch. With a vehicle in good working order, the fluid coupling can only add to its efficiency, because it's entirely automatic in operation and requires no skill on the driver's part in engaging engine power smoothly to the driving wheels. Another advantage is that although there is slippage within a fluid coupling, the absence of engaging mechanical parts minimizes wear due to this cause, which is not true of a conventional clutch. However, slippage builds up heat within the unit. As the temperature of the oil rises, the oil pressure builds up also. Therefore, if the fluid coupling is to do its job efficiently, it must be kept full of oil, and the oil inside must be kept within a prescribed temperature and pressure range. When heat and oil pressure increase, it is necessary to cool the oil. A circulating system with a reservoir and oil cooler is provided. The oil from the reservoir is delivered by an oil pump to the fluid coupling. There, the operation of the coupling keeps the oil circulating. Besides being kept at full supply within the coupling, the oil must be kept at the proper pressure. When it goes beyond the prescribed pressure, a spring-loaded check valve at the central passage or oil exit of the coupling is opened by the excess pressure. The oil exits to return to coolers in the transmission's reservoir. and when the oil pressure is lowered to within its prescribed limits, the spring closes the check valve again. Highly efficient, the fluid coupling is a boon to vehicle and driver, adding to their efficiency, saving wear and tear on both, even during the most rugged of military missions. Yet the basis of its operation is almost as simple as that which causes this, the force of a liquid under pressure. Straight radial veins in both the pump and the turbine cause vortex motion. Rotation of pump and turbine adds another motion. This dual motion of the oil combining to send it in this direction. Increasing the velocity of these flows eventually transmits the torque, or turning power, from the engine through the fluid couplings pump via the turbine to the drive wheels. When used in place of a conventional clutch, the fluid coupling is an effective liquid link between the engine and the drive wheels.